Welcome everyone to our course. Today we will have 5th week and first module. Now so far we had started discussing about different generations of the solar cell. We discussed about first generation solar cell and you have seen there we studied about single crystal silicon solar cell, and in second generation solar cell we talked about amorphous thin film solar cell. Then we started the third generation solar cell. In last few lectures we started one of the third generation solar cell, namely dye sensitized solar cell or DSSC devices, and we have seen that how to fabricate a DSSC device in the lab and what is the photophysics or the working principle behind the dye sensitized solar cell. Now in this context we will today discuss about another very important variety of the third generation solar cell, namely organic solar cell. Now as you can see from this picture, this is an example of an organic solar cells. Now looking at this picture, some of the facts which immediately come to our mind is that we can fold this solar cell. So that means this kind of solar cells are flexible, and also as you can see from the figure, these are transparent. So that means light can transmit through them. So imagine we decorate our building in such a way so that the every walls of our building is transparent, but still we can do our indoor lighting using those transparent window, which is now behaving as a solar cell. So organic solar cells provide some of the advantage or benefits over the conventional solar cell in terms of flexibility, lightweight, compactness as well as the transparency. Now there are some important factors or important considerations has to be taken into account before we start about the organic solar cell. Now our everyday account to any kind of organic material, for example if we take a water bottle, a mineral water bottle. Now this is also made of some kind of polymer, right. What kind of polymer? Maybe some kind of polystyrene or crossed polystyrene. But if we touch this water bottle, we know that we never get an electric shock. Why? Because this kind of plastic does not conduct any electricity. But what will happen, let us say if this water bottle which we use for drinking the water also contains electricity. So it is not long back that three scientists namely Sirakawa, Alan J. Heger and McDermott, so they discovered that there are some class of organic materials or some class of polymeric material, more specifically they can conduct the electricity. Now these polymers, they have alternative single bond and double bond in their backbone or structures. This kind of polymers, since they conduct the electricity, they are called conducting polymer or conjugated polymer. Now once it was discovered that this polymer can also contain electricity or they can also conduct electricity, so then rapidly people were interested to see whether we can make any kind of optoelectronic devices using this polymer. For example, whether we can make a solar cell or light emitting diodes using this conducting polymer. Now obviously there are certain advantages of using conducting polymer over the inorganic materials. For example, in any kind of organic material or conducting polymer, we can tune their optical properties, we can tune their electric properties and sometimes their mechanical properties also. And also these conducting polymers are flexible, so you can make it on a flexible substrate. Inorganic semiconductors like silicon or gallium arsenide do not provide us this kind of opportunities. So there usually we use some mechanical rigid substrate and we can't make it on a flexible substrate. And also tuning the optical properties is very difficult in inorganic semiconductors. So because of this advantage, very soon organic materials take the pace and it replaced some of the important applications in modern days optoelectronics devices, and that begins the era of organic solar cells. Organic semiconductors, this is a very special class of semiconductors which is made out of organic materials. Now it combines the virtue of the plastic with those of the semiconductor. Now when we talk about plastic, so plastic has plasticity, that means it can fold, it is flexible. So if the semiconductor has all the properties of a semiconductor, in addition to that if it is also flexible, then it will be very useful for making any kind of devices. The second important properties of this organic semiconductor is high optical absorption coefficient. As you have seen that if the absorption coefficient is very high, so the light absorptions per unit length is also very high. Third thing is that you can tune the properties with flexible synthesis methods. As you can see in this figure, we have a panel which contains 3 different films. One is blue color, another is greenish, another is the red color. These 3 different films has made on a flexible transparent substrate and using the same material, same organic semiconductor, but by changing their synthetic protocol, we can change their structure, we can change the side groups, and that significantly change its optical emission properties. That is why we see different colors here. For example, here also we are showing like 4-5 different varieties of the same semiconducting tube which emits at different color. One is at red, another is at yellow, another is at white, something is blue. So, by tuning their optical properties, by changing the synthetic protocol is much easier in this class of organic semiconductors. So, this is one of the major advantage of organic materials. And also the fabrication cost is low. Sometimes the precursor material is costly, but if you look at the overall synthetic procedure in comparison to the inorganic semiconductor processing, which always involves very high temperature and the yield is very low, this kind of materials can be synthesized at room temperature and at moderately low temperature also, and yield is moderate to high. Some of the other characteristics features of the organic solar cells are mechanical flexibility. As you can see in this figure, we can hold the solar cell in our hand and we can bend it, that means this is flexible, and we can put it on any flexible substrate. These are lightweight, so these are compact devices. Their cost of production is also low, and finally the power generation efficiency is also very high under the low light intensities. This is very important. So, especially because of these reasons, this kind of solar cells are useful for indoor lighting, like for the room decoration purpose or for any kind of small hall or stadium decoration purpose. This kind of solar cells will be useful. Now, the power generation efficiency of these organic solar cells is of course not as high as the crystalline silicon solar cell, but it is improving by changing the geometry of the polymer, by changing their absorption properties and also the synthetic protocol and the self assembly protocol of the device. Now, we can broadly classify the organic semiconductors into 2 different categories. First is the conjugated polymers. Conjugated polymers are a class of materials or a class of polymers which shows alternative single bond and double bond in their backbone, and because of this kind of structure they can conduct electricity. Second example is the small molecule organic semiconductors. So, here the molecular weight of the organic semiconductor is small in comparison to the conjugated polymers. We will discuss about these 2 different types of the organic semiconductors in our lecture today. Now, in this context, let us introduce some of the terminology which we use in organic semiconducting material. In the inorganic semiconductor, we use conduction band and valence band, CB and VB. But here instead of CB and VB like inorganic semiconductors, we talk about the LUMO energy level and HOMO energy level in organic semiconductor. Now, we already mentioned it earlier also, the word LUMO that stands for lowest unoccupied molecular orbitals, and the word HOMO that stands for highest occupied molecular orbital. So, as you can understand, the LUMO corresponds to the conduction band and HOMO corresponds to the valence band. So, the same thing as valence band and conduction band in an inorganic semiconductor is the HOMO energy level and LUMO energy level in an organic semiconductor. Charge carriers in organic semiconductors are called polarons. Now, these charge carriers, they always generated in a bound state. So, the electrons and holes which are bound together, but by some kind of force, that are collectively called excitons. So, in organic semiconductors we very often use excitons. Exciton is the bound electron hole pair. So, I repeat, exciton is the bound electron hole pair. Now, since exciton participate in the charge conduction in this kind of material, sometimes this class of devices are also called excitonic devices or excitonic solar cell. And also electrons are localized in the materials, unlike semiconductor, unlike inorganic semiconductor like silicon, where the excitonic binding energy is very low and the charge carriers are free to move around or roam around inside the materials. So, the electrons are delocalized in inorganic semiconductor, but because of the high binding energy of the excitons, electrons are localized in this kind of material. We have to provide some kind of external perturbation in terms of energy, either by light energy or by thermal energy, to dissociate this bound electron hole pair. Now, on the right hand side we are showing some of the very popular structure of the small molecule and the polymer class. For example, a small molecule which is used commonly in fabricating device is the pentacene. So, penta stands for the 5. So, as you can see here, there are 1, 2, 3, 4, 5 benzene ring which are fused together. Similarly, we have another common structure called rubrene, and another very commonly used small molecule for fabricating device is PCBM. Now, C60 or fullerene, which is also called buckyball, that has a spherical football like structure like this. But the C60, if you remove this part from the compound PCBM, the rest of the part is C60, but the solubility of the C60 is not very high. So, that is why if I wanted to make a film of the C60, what we have to do is that we have to deposit it by vacuum deposition technique. But let us say I wanted to make this C60 film by a solution based approach. So, then we anchor or we conjugate a side group, usually an alkyl group, along on the fullerene moiety, and what we get is the PCBM. So, the solubility of the PCBM and the absorptions of the PCBM is much higher than the C60, and this is a common material of the choice as an acceptor material in organic solar cell. Now, let us come to the polymers. Like there are different class of the polymer, and the structure inside the bracket, that is the backbone or the moiety of the polymer, and depending upon the structure or the moiety, the polymer nomenclature is done. For example, this kind of structure where you can see that there are 1, 2, 3, 4 and 5 coordination sites are there, and there is a sulfur which has replaced this 5 kind of coordination site. This kind of unit is called a thiophene unit. Now, in this thiophene unit we have put a hexyl group as a side group. Now, this group inside this circle, this is called the side group of the polymer, and the main backbone or the main moiety of the polymer is this group. So, the role of the side group is just to solubilize the polymer or to increase the solubility of the polymer in organic solvent. So, if I do not take the N, so what I will have? I have a thiophene backbone along with the alkyl group as a side group. This is an example of 3-hexyl thiophene, a monomer of this compound. Now, if we put too many of them together, then what I will write the formula, I put a bracket and then I put the sign N, where N is a large number. Then this kind of compound is called poly 3-hexyl thiophene. Now, depending upon the value of N, like let us say if N is equal to 1, so then it corresponds to only one repeating unit of the structure. So, that we call as a monomer, where N is equal to 1. Now, if N is equal to let us say 2, 3, 4, then it is not big structure, but not also a single unit structure. This kind of structure we call it as oligomer, where the values of the N is 2 or 3 or 4 like until 5 like that. But if the values of the N is very large, like let us say N is greater than 50, then we have so many repeating units of these structures, and that we call it as a polymer. And it is interesting to know that in the case of the polymer, the optical properties and the electronic properties pretty much repeats after N is equal to 6 units. Now look at the other polymers called poly p-vinyl phenylene or PPV. Here also there is a unit or the backbone which is inside the bracket, and if you make a many of this p-phenylene vinylene, then you will get poly p-phenylene vinylene. And similarly, you look at the next structure polyfluorone. Here the structure inside the bracket, this part, that we call as a fluorine. It is a highly fluorescent compound. Now if we make many of this fluorine unit, then I put a bracket and I put the symbol N, where N is a large number, then we call it as a polyfluorine. Now all of this structure, whether it is a poly 3-hexylthiophene or poly p-phenyl vinylene or it is polyfluorine, all of them has a conjugated backbone. So it means that it has an alternative single bond and double bond. As you can see in this thiophene backbone, first we have a single bond, then we have a double bond, then we have a single bond, then there is a double bond. Similarly here we have an alternative single bond and double bond. Because of this kind of structures, electrons are delocalized on these conjugated backbones, and that helps them for the conduction of the electrons. Now this compound poly 3-hexylthiophene is also abbreviated as P3HT. This is a compound which is very commonly used in fabricating solar cell along with PCBM, and this compound, this P3HT, is used as a donor polymer, whereas this PC60BM is used as an acceptor molecule. Now why we need these two different kinds of molecule, that we will discuss later on. Similarly, this poly p-phenyl vinylene, this is also called PPV, and polyfluorone, this is also an example of a conducting polymer which is highly fluorescent. Now we can use the pair of this polymer and the small molecule depending upon their energy level as a donor and acceptor material in this kind of solar cells. Now polymers generally insulating. If you touch your drinking water bottle or your Coca-Cola bottle, usually you do not get an electric shock. Why? Because this kind of material does not conduct the electricity. But if you insert the alternative single and double bonds inside the polymer structure, what you call as a conjugated structure, then the polymer will be able to conduct the electricity. For example, you look at this structure, here I have a alternative single bond, then double bond, then single bond, then there is a double bond. So double bond is represented by this 2 line and the single bond is represented by the 1 line. This kind of structure is called a conjugated structure. So this is called conjugated structure, and this kind of polymer is called conjugated polymer. Now what will happen in this kind of conjugated structures, the pi electrons which looks like a dumbbell shape, which is distributed over this polymer backbone, they are delocalized into the clouds above and below the chain. So the pi electron density they distributed throughout the polymer chain above and below. So because of these conjugations, this kind of polymer have a delocalizations of the electron clouds or the pi electron clouds or pz electrons which is loosely bound throughout these chains. So if we wanted to calculate the probability of the electron, so the probability density is quite large in this kind of polymer, and band gap is suitable for absorptions of the sunlight. So the band gap of this material is suitable to absorb the light in visible regions, or we can even tune some of the materials to absorb it in near air region or even in UV region. Now if we cross section or if we look closely into the structure of an organic polymer solar cell, then depending upon the junction type, we can distinguish the organic polymer solar cell either as a single layer solar cell or a bilayer solar cell or a bulk heterojunction solar cell or a graded heterojunction solar cell or a continuous heterojunction solar cell. Now a single layer device, as the name suggests, there is only one particular kind of material is there, either donor or acceptor material, usually a donor polymer. So as a donor polymer, like for example, you look at the structure of these devices where this is a sandwich type of geometry. I have two electrode 1 which can be a tissue transparent conducting oxide like ITO, indium doped tin oxide, or any kind of metal, and there is another electrode at the back which is electrode 2 which is usually made of any kind of metal like aluminum, magnesium and calcium, and between these two electrode we sandwich the organic electronic material which can be a polymer or small molecule. So, whatever the charge carrier which have been generated here, whatever the charge carrier that has been generated inside this organic polymer, which is also called the active layer, they will be separated depending upon the voltage difference of the electrode 1 and electrode 2. So, this kind of structure is a sandwich structure where we sandwich the active layer, which is an organic polymer or a small molecule between these two electrodes. Now, if you use only one particular kind of material, it is a single layer device. Now, if you use two different materials, like here we are using two materials, one is the electron donor and another is the electron acceptor. Both are organic materials, but one is electron donor, so that donates the electron, another is the electron acceptor which accepts the electron, and the electrons will flow now towards the downward directions and the hole will go to the topward direction. So, that is an example of a bilayer devices. But we can also mix the electron donor and electron acceptor throughout this active site. So, instead of making this layer by layer, we can also mix them together and we can make an active layer out of this mixture, and in these mixtures the donor and acceptor is distributed in a dispersed conditions, and that is an example of a bulk heterojunction solar cell. As you can see in the figure, there are two different color shade we are showing. One is due to the donor, another is due to the acceptor, and this distribution is non-uniform and it is distributed throughout this active layer. This is an example of a bulk heterojunction solar cell. Similarly, we can have like a graded heterojunction like here, like where you can see that a particular concentrations of the donor and a particular concentration of the acceptor gradually changing along the thickness. And we can also further optimize this device by putting an electron blocking layer or a hole blocking layer. Now, the electron blocking layer, which is also called like EBL, and the hole blocking layer, which is also called HBL, the role of them is to block one particular kind of charge carrier and allow the other charge carrier. So, basically they act like a filter. For example, if you take an electron blocking layer, so the electron blocking layer or EBL layer that blocks the electron to flow on this side, but allows the holes to flow on that side, or the hole blocking layer or HBL that allows through hole to block and flow in this side and allows the electron to flow in this side. So, the role of the EBL and HBL is to preferentially allow one particular charge kind of charge carrier over other things. So, that helps to increase our short circuit current. So, these are different class of solar cells. Now, there are two different class, especially these bilayer devices and the bulk heterojunction solar cells, they have been studied in details in organic solar cells. Now, we have talked about the active layer. Now, active layer is made of the active layer materials. Now, what can be active layer materials? They are usually a hole transport material or an electron transport material. So, as the name suggests, the hole transport materials are those material which are have a good hole transport properties or their hole mobility is high. For example, it can be a conjugated polymer like this, you can see the example here, or it can be a conjugated dendrimer or small molecule like this. So, also these small molecules can comes together and can make a spherical kind of geometry which you call as a dendrimer. So, it can be a conjugated dendrimer or a small molecule. Now, electron transporter or electron acceptor, so basically these are the compounds which can accept the electron and whose electron mobility is very high. For example, fullerene, we just discussed about fullerene. So, fullerene is C60. So, as I said that if you remove this part from this structure, so this is C60, and when I add this side group which is an alkyl side group, then I call it as PCBM. And why we put this side group here along the C60 chain? To make it solubilize, so that the solubility of this compound increase. Or even we can use different nanocrystals like metal nanocrystals or carbon nanocrystals as an acceptor materials. For example, we are showing here an ACM image of nanocrystals, and you can see that we can find out each and single nanoparticle separately, and the electron mobility of these nanocrystals is also very high. So, when we make the device or when we make the active layer, we have to mix the hole transport layer with the electron transport layer. That means, we have to mix the conjugated polymers with the fullerene or conjugated polymers with the nanocrystals. Similarly, we can make the conjugated dendrimer or small molecule with the fullerene and conjugated dendrimers with the nanocrystal. Let us try to look at the working principle of organic solar cells. Now, as the organic solar cell, just we have said that it is a sandwich device. So, basically we have two electrodes, one is a transparent ITO substrate which is deposited on a glass substrate here, and then there is this metal electrode aluminum, and you can see that we have put this metal electrode as a finger electrode to reduce the leakage loss, and in between there is an active layer, and we can use a hole blocking layer or electron blocking layer in between, like we are using P dot PSS, which is again a polymer which hole mobility is very high. So, it actually stops one kind of charge carrier over other, and another thing P dot PSS does here is that it helps to weight the surface, so that the films on this substrate becomes very uniform. Now, if we load this active layer, you will see that this active layer is made of two different compounds, one is donor and another is the acceptor material. Now, we already said that as a donor we can use a conjugated polymer, and as an acceptor we use a small molecule. Now, what will happen, like this is the donor molecule, okay, and this is our acceptor molecule. Now, when the light falls on it, what will happen, the light passes through here, and the electrons they excite it from the ground state or the HOMO to the LUMO level of the donors, and that electrons now transfers to the acceptors. From there it goes to the cathode. So, what it left at the donor is the whole molecule, and it goes to the anode. So, using the outside circuit, it comes from the anode to the load, and the electron which comes to the cathode, using the outside circuit it comes to the outer circuit, and you get a current in the output. So, today we learn about what is the active layer, or what is the some principal characteristics of an organic solar cell, how to fabricate a organic solar cell, and we have learned that there are certain advantages of organic semiconductor like flexibility, compactness, tunability as well as high efficiency over the inorganic semiconductor, and that is why organic semiconductors are preferred to make solar cells for indoor lighting or for flexible substrate based structures. And we have also seen that conjugated polymers and the small molecules, they are used to make these organic solar cells, and there can be different kind of solar cell like bilayer device or bulk heterojunction device or grade heterojunction device or continuous heterojunction device. Out of that bilayer device and grade heterojunction device, these two are very important class of this organic solar cell device, and in the next lecture we will discuss in details about these two different kind of solar cells, bilayer solar cells and bulk heterojunction solar cells, and we will also discuss about what kind of morphology and photophysics is optimum or required for getting maximum efficiency in this kind of solar cell. Thank you very much.